Welcome back. Most scientific research, including social science, is deductive. That is, once a scientist has a research question and has familiarized herself with past literature that's relevant, she builds a hypothesis that can be operationalized as a testable prediction. Today we'll learn about the most common approach to this testing. It's called Null Hypothesis Significance Testing, or NHST for short. While NHST has its flaws, and there are alternative paradigms for testing hypotheses, it continues to dominate scientific literature. For every hypothesis to be tested, NHST requires a second hypothesis. To understand why, think back to what you know about confidence intervals and how we talked about them. The confidence interval of a mean, or a proportion, is the range within which a certain percentage of similar-sized samples from the same population are likely to fall. We need these because the probability this sample mean precisely matches the population mean is disappearingly small. Imagine trying to find a sample of 2,000 Americans with mean income exactly equal to the true mean income in the US population. But when we compare confidence intervals to a criterion, for example, to decide if an investment was likely to pay off, we ask the question a little differently. Instead of, is my sample mean correct, we might ask, based on our sample, is the probability small enough that the true mean return on our investment is less than what we're willing to risk? That is, the question that turned out to be of interest was not about the mean, it was about how certain we could be that the mean is greater than our criteria. In fact, very often what scientists want to know about is differences. For a drug trial, we want to know if symptoms improve more than doing nothing or giving a placebo or other existing treatments. If we want to study gender and pay, we're asking about the difference between male pay and female pay. If we're investigating the relationship between height and longevity, we want to know if the relationship is zero or if something is there. Think back to the master equation for a second. Outcome is model plus error. That model statement can have one or a series of b or beta parameters that represent mean and other effects of other variables. Now, what happens if the model or an element of it is zero? It falls out of the equation, right? It's ignored. And that zero has a specific meaning. A test statistic, like a z or a t-value, is a ratio of signal or effect to noise, that is, error. When a test statistic approaches zero, it's because the estimate of the element being tested, a difference in means and effect and so on, is small in relation to the total amount of variability or standard error. If you look at hypotheses in published papers, they most often require a yes or no answer, and require not only estimates of a statistic such as a mean, but estimates of uncertainty. Just like proving that your estimate of a mean is correct, it's difficult, if not impossible, to prove that differences in pay by gender are the result of discrimination. An observed difference could be due to sampling. There could be a different factor linking gender and pay, such as hours worked. There are endless scenarios. But it is possible to look for evidence against a theory or a hypothesis. As a result, even if we hope to find that our hypothesis is true, we have to try to break it. Test if or when it doesn't hold up in order to prove much of anything. For example, suppose a toy manufacturer wants to find out whether a new doll is sturdy enough to be played with. Would they put it on a shelf in its box for a year and see if it survived? Of course not. They would try to create a stress test by either creating or mimicking the most potentially destructive ways the doll is likely to be treated. They could give one doll to a room full of hungry and tired 3-year-olds for an hour. They could use tools designed to measure, for example, how much force it would take to pull the arms off. They could send them home with a mix of 1,000 kids for a month that measure various kinds of wear and tear. This last one is perhaps the best example of the three for thinking about null hypothesis significance testing, because not only is it a stress test, but it allows the use of statistics to draw conclusions about the probability that the doll's durability will be a problem. What the manufacturer is testing in this situation, the null hypothesis, is the hypothesis that the doll is too fragile to meet consumer expectations. What they really want to know is whether their expectation that the doll is ready to go to market that's the research hypothesis, is true. The research hypothesis will always be the hypothesis you've made. In a paper, it would have been stated as explicitly as possible in the theory and hypotheses section. In our discussion of the scientific method, we labeled the research hypothesis as a prediction, as opposed to a hypothesis, because it took a general theoretical hypothesis and operationalized it into a testable form. Sometimes you'll see the research hypothesis abbreviated as H1 with the 1 subscripted, although you should be careful, as papers with multiple hypotheses may number them hypothesis 1, hypothesis 2, etc., each of which is its own distinct research hypothesis. The null hypothesis, that's the one we test, is the complement of our research hypothesis. Notice I didn't say opposite. If the research hypothesis, or H1, is that college costs increase over time, the null hypothesis, H0, is not that they decrease, but they don't increase. In logical terms, to evaluate a research hypothesis X, we test a null hypothesis, not X, to find out if there's sufficient evidence against the null hypothesis to decide whether to reject the idea that not X is true. When stating the results formally, we would frame a significant NHST for a difference, something like, based on sample Z, we reject the null hypothesis of not X with at least P certainty and find a statistically significant difference between group A and group B on variable Y. There's a lot in that. Based on sample Z, so we give some information about where we're getting our information, we reject the null hypothesis of not X. We're stating what we're actually testing with at least P certainty, our significance level, and find a statistically significant difference between each group on the variable. The language for a non-significant result is a little more unwieldy. Instead of reject, we say we fail to reject the null hypothesis. We do not ever accept a null hypothesis. That's why we need null hypotheses at all. Put together, we could say, based on sample Z, we fail to reject the null hypothesis of not X with at least P certainty, and we do not find a statistically significant difference between group A and group B on variable Y. Notice that just like we don't accept the null hypothesis, we also don't conclude there is no relationship. All we can conclude from a non-significant null hypothesis test is that the data in our sample don't provide sufficient evidence for X that we're willing to conclude it's not the result of random sampling variability. Now, go back and watch that again if you need to. And once you understand the words I just said, the best thing you can do to try and deeply understand the idea is to go out, find some hypotheses, and try to make formal research and null hypotheses, and state the results for what you would say if you were to reject or fail to reject the null hypothesis. Your hypotheses don't have to come from peer-reviewed journals. You could design a null hypothesis test for the statement, central cities have better bus service than suburbs, or sisters are better than brothers. My only caution is that the less clearly operationalized your hypothesis is, so in other words, if it hasn't moved from theory to prediction, sisters are better than brothers is a good example, it can be difficult to figure out the language. Now, there are alternatives to NHST, and there are valid critiques, but it remains the central paradigm for statistical testing in the social sciences, so it's important to know about and know how to use it. That's all I've got for now. Today, we covered the ideas of reporting, the idea and the reporting of null hypothesis significance tests. Next time, we'll talk a little bit more about numbers and details. Thanks for watching.